the voice is produced by vocal folds. And vocal folds are nothing but a constriction in our larynx. They were able to generate the normal cries, but also chaotic cries. All these crazy sounds. This was just a small example how the crazy East German politics was even in '88. I recommend that you make a photograph of this. Do my best. Let's start with the current status. So right now I'm a professor for theoretical biology at Charité and Humboldt University. I started a while ago with physics, studying physics at Humboldt University. Before I was grown up in northern Germany, in Güstrow. And now I have 2 children. I'm married 40 years or so. And I live now in Berlin for many decades. And I teach. I love to play beach volleyball or volleyball in general. I have 4 grandchildren. That's about me. In my eyes, biology, medicine has to fulfill the laws of physics and chemistry. So it's not out of natural sciences. That's why all the laws of physics and chemistry are valid and relevant and interesting. But there is something special about life. And one aspect is the high complexity. So it's extremely complex, and that's why the rules of physics and chemistry have limited applicability. This is one major effect. The other point is that life is in some sense a mixture of natural science and of history. Since life evolved over billions of years, and it only makes sense to understand the current life with a view to the evolution of life. So that's why many other forms of life, many other decisions might be possible. And that's why you have to add the historic aspect to life if you want to understand biology or medicine. And this is different from physics, where at least most people believe that the laws of physics are valid at any time and everywhere in our accessible universe. That's why I studied physics, but while studying physics, I realized that other areas like biology are even more exciting, and I moved slowly from hardcore statistical physics to interesting, complex biological systems. Leonor Michaelis, he established a group at Humboldt University where interdisciplinary research was the topic. So he was interested in self-organization, dissipative structures, second law of thermodynamics, synergetics, all these interesting topics. And most students in the group had different topics like stochastics or nonlinear dynamics, pattern formation. And I became interested in stochastics and random noise and then deterministic chaos. And then I had all the freedom to explore what I found interesting, but I was also inspired by my colleagues working on artificial neural nets or pattern formation. So I was surrounded by interesting young people with a broad range of interests, and that's why the switch from physics to biology was at the end quite natural. So I finished my diploma studies in '84, and since I continued with a similar topic, I could start right away with my PhD studies in the same group of Werner Ebling, and I finished it in '86, so 2 years later. In the '80s, people became interested in complex systems, and if data are very complex, like brain data or climate data, biological data, then there are at least 2 alternative explanations. So everything is random, it's stochastic, or there might be something called deterministic chaos. This was a new development in the '80s, that deterministic chaos can explain complex behavior. The butterfly effect is the most popular example. And in my diploma thesis and PhD, I was interested, can you distinguish between stochastic process or noise and deterministic chaos from data. So it was clear that the theory of deterministic chaos was finished in 84 to 90%. That's why it was hard to improve the theory, but the applications were still not clear. And in particular in biology and biomedicine, people claimed a lot that heart rate data are chaotic or brain data are chaotic, but it was never proven. That's why my main interest became to apply the well-established theory of dynamical systems, of chaos theory, to real data to answer the question, can we learn something from, say, theoretical concepts to the real world, to biological or medical data? So including circadian rhythms, so day-night rhythms, or heart dynamics. But perhaps my earliest first interest was voice production. So we all know that the voice is generated in the larynx here, and it's interesting, important, but not so easy to understand from a physical point of view. So it's relatively easy to explain a sustained vowel, that's a sound that is periodic, regular, but requires already an interplay of mechanical oscillations of the vocal folds and aerodynamics, the airflow from the lungs to the mouth. And this brings together an and this was clear in the 70s, 80s. This was not new. But many speakers also speak like and this sounds strange, and it's not so rare. So in singing, Louis Armstrong, or in patients, it's common observation that the clear voice might be interrupted by a rough voice. And this was widespreadly found, but never very well explained. And this became my niche, since I learned irregular voices might be related to nonlinear dynamics, to chaos theory. And this was the starting point, say in 87 or so, to switch from hardcore physics to the first biomedical application. Let's go back to my own PhD thesis in 86. So I realized deterministic chaos is interesting, but the theory is well developed and I can only make minor contributions. But then I encountered, by chance, Kathleen Wermke. I was surprised, excited how relevant deterministic chaos can be in acoustics. And it was told to me by Werner Mende earlier that newborn cries might be an application of chaos theory, but this was abstract, and I ignored it. But then I had to go to another building, in Berlin-Pankow, since our own computer was broken. It was a Hewlett-Packard computer, 9835 or 45. I don't recall, I used both types. And getting reasonable computers in East Germany was not so easy. And we were happy to have such a Hewlett-Packard computer. But since I had to do some plots, some graphics, I had to go to Berlin-Pankow. And then Werner Mende organized that I met by chance Kathleen Wermke. And she showed me her thesis, PhD thesis, and it was full of recordings and spectrograms of newborn cries. And I was excited to see that newborn cries did what we did in labs. They were able to generate the normal cries, but also chaotic cries, all these crazy sounds, and people might used to it, and it's very common. But to me, it was a breakthrough that, say, in the real life, nonlinear phenomena happen all the time. And that's why I started to change my topic. So I learned acoustics. I went to biomedical applications of nonlinear dynamics, and so I realized that I can contribute to this field, and not only for newborn cries, also for patients, for singers, and later for animal voices in biology. Starting point is that these phenomena are not rare. In normal languages, in patient data in newborn cries and in animal vocalizations. This is the starting point. Since if you have a theory about something nobody cares, this is not very exciting. And the next step is that the terminology was confusing. Mostly voice analysis has been done by engineers and medical doctors, and they were very strong in linear systems and in anatomy and physiology. But my education in nonlinear dynamics was distinct. In medicine, they had many terms: diplophonic, dichrotic, hoarse, rough. All these were terms describing chaotic voices. And I could provide a relatively simple theory that this is all related to limit cycles, period doubling, deterministic chaos, and it can be analyzed with phase-space analysis, with spectrograms, bifurcation theory, and so on. So it was at the end a kind of simplification of the data with a common theory. And this was the starting point. And then we went to experimental work with excised larynx studies. We did computer simulations. We developed the theory. And in fact, this was indeed, together with colleagues from Iowa City, the starting point of a new research field. And that's why in 1990, I decided this will be my main research topic in the next 10 years, perhaps in my whole career. So this is this beautiful campus here in the middle of town was originally the veterinary campus of Humboldt University. So it's older than the university itself. And say just 30 years ago, you had pigs and horses here on campus. But now the veterinary medicine moved to the south of Berlin. And now these buildings are used mainly by biology and medicine. And still students like it a lot. We like it as teachers. We have beautiful lecture halls, offices, and a good atmosphere to relax in between. So there was a debate whether or not languages are allowed to enter the campus or biology. And there was even a vote in the academic senate of Humboldt University, and there were two options: languages or biology is allowed to join the campus. And there was I guess 13 to 12 voting that biology is allowed to join the campus. And this was very nice for us, so we could reconstruct many of these buildings, and now biology is here in the center of Berlin. So chaos is a word that is used for everything, but deterministic chaos is part of a well-defined theory termed nonlinear dynamics, and it's described mathematically in a strict sense. And many people confuse it with the everyday chaos. And that's why if a movie uses the word chaos, it's not implying that it's on nonlinear dynamics or deterministic chaos or chaos theory. So I mentioned Louis Armstrong. We had also a collaboration with Michael Edgerton, and we compiled many data sets with chaos in the voice from modern singers. But frankly speaking, I'm more interested in classical or regular singing, and sometimes in jazz, and the rhythm in jazz is also exciting, but rarely chaotic. Right now we submitted a paper on a heavy metal singer, and he is using a lot of chaos, but I'm not really interested in his music, but I'm more interested in the mechanisms of such voice production. That's why there's a gap between my research and my musical interests. Our immune system is quite essential, but there was an old wrong theory by Abderhalden about so-called Abwehrfermente. And this theory was adopted by Leonor Michaelis, but he was politically so strong in, say, 1918 or so, that Leonor Michaelis had to leave the country to make a continuous scientific career. Nevertheless, Leonor Michaelis became famous due to the discovery of the Michaelis-Menten law, and Abderhalden is forgotten. And nevertheless, this old building was named after Abderhalden until the 90s, but we changed it now to the Leonor Michaelis house. And the whole story is written here. It's about the old wrong theory of Abderhalden, and the correct explanation of our immune system by Leonor Michaelis. You see the traces. So my research is focused on rhythms. So I was trained as a physicist to describe planetary motion with the planets oscillating around the sun. Then, as I discussed earlier, I became interested in voice production. You see, the voice is produced by vocal folds. And vocal folds are nothing but a constriction in our larynx and driven by airflow coming from the lungs to the mouth. And these vibrations are again mechanical oscillators. So if I say ah, this implies that I have a sound of 100 hertz roughly, and the period of the vocal fold vibrations is just 10 milliseconds. So very, very fast. But later in the 90s, mid-90s, I became also interested in heart rhythms, since also heartbeats and respiration are quite important and complicated. And here the period is more in the order of 1 second. So we have about 1 second per heartbeat or 60 beats per minute, as we might know. And later, after 2005 or so, I started to become interested in chronobiology. So the chronobiology, or the circadian clock, is a theory about rhythms that are close to 24 hours. So the period is now much longer, about 1 day. And this implies that these rhythms also control sleep-wake cycles. If you go to bed in the evening, this is part of the rhythmicity. If we are active in the morning, that's part of such rhythmicity. And it's interesting that we realize these rhythms are generated in our bodies autonomously. So without external drive, for example, from the clock or from alarm clocks or from lecture series, we have an intrinsic rhythm. And the generation of these rhythms and the coordination with the sun, this is part of our research interest. And after all, I was doing all the time rhythms, even by changing topics from planetary motion to circadian clock. So it's hard to imagine the situation in the 70s and 80s. So you might have learned that the rules were quite strict. There were many hopes, but the situation was very bureaucratic, and old men more or less dictated what was allowed to say, what's happening, how the economy develops. And the problems were obvious, but there were many dogmas in the political world. Gorbachev was the first one in about perhaps 85 or so, frankly speaking about the problems. And this was already a major change of politics, that the problems are named probably. And that's why we were reading all the articles published on Gorbachev, all his speeches, and we were really excited by the openness, by glasnost and perestroika. And glasnost more or less means openness of the discussion, and perestroika means let's change the society. And these were really key words in the late 80s, and we were all optimistic that something will change. But it took a while, it took a few years until things changed also in East Germany. Science in East Germany was good, since we had at least libraries, we had some computers, and we had a lot of freedom at universities, since basic science was not so much influenced by old-fashioned politics. That's why personally I felt in a good environment at Humboldt University in the 80s in the group of Werner Ebeling, and I could do interesting topics. There were still limitations, so the computers were not up to date and copy machines were rare, but the main limitation of research in East Germany was the daily exchange with colleagues from all over the world. So we were rarely allowed to join conferences, and that's why we were a bit behind from the latest developments. And this was not so much a concern of mine since I was still young, about 30 years old. That's why I couldn't say that my career was strongly limited by the East German situation. But after the wall came down, I was traveling immediately to Denmark, to the US, to all countries, to all conferences, and I enjoyed it a lot. This was a strange situation. It was still at Moscow University, but it was not allowed for East German students to have contacts to other people than Soviet Union students and, East German students. And this was to me so much outdated that I ignored the rule totally. But at a meeting of all East German students, I learned that it's forbidden. And in particular, a female student had an African friend, and this was punished by authorities. And I was so ill, so crazy, that it was not allowed to have a friend from Africa, that I was shocked at these days. This was just a small example how, crazy East German politics was even in '88. Interestingly, copy machines were rare, and there were different reasons. First of all, the economy was weak, and it was hard to produce high-quality copy machines. But the second reason might be that the government was afraid that people copy Solzhenitsyn or other critical books. No? And that's why when I read that we need 3 copies to submit a paper to Physics Letters, no, I had a problem. No? I went to the library, and the library said, oh, we are not allowed to make private copies. No? And then I went to the ministry, since my aunt, she was working in the ministry building, and she was able to do some copies that I could submit the paper to Physics Letters. This was later accepted and published. We had economic and political problems, but we found in many cases some ways to solve them. The exchange between Eastern and Western scientists was complicated, but not impossible. First of all, we attended all meetings in Budapest or Eisenach, as some Western colleagues attended, and this was one option to get to know them personally. Another option were so-called cards. We asked for cards, on cards, to send us reprints. So if we realized in some databases that there is an interesting paper, then we could send a card to the colleagues, typically written, could you please send us the latest paper in Physica D and related papers. And the colleagues were so kind that they sent us all their papers at the end in big, thick envelopes. And this was exciting since we got modern preprints early enough to use them for our own science. And I sent also such cards around the world and was proud if Jack Hudson, a colleague from Virginia, replied and sent me his papers and greetings. Later he became a good friend of mine, and this was funny since he lived in West Berlin and then he visited us in East Berlin, and then he had to get money, or he had to exchange Western currency to Eastern currency, and that's why he was happy to spend the beer in a restaurant. And later he became a reviewer of my second thesis. So, and this was fun to have an American friend even before the wall came down. While I was still a diploma student, I was allowed to give a talk at an international conference. It was on the Wartburg castle about chaos, and in addition to our colleagues from Berlin and other cities in East Germany, there were also good friends from Bremen, Peitgen, Richter, Plath. And so we had a nice conference on chaos and fractals. But in addition, there was a German history to have a singers contest on the Wartburg. And since East Germans and Russians love to sing at meetings, so we also celebrated the singing at the Wartburg castle. And at the very end, there was even a prize for the best singer. And the funny coincidence was that Peter Richter, he gave a lecture on fractals. And some of you might have heard about fractals, and that there are these apple trees that look like a fractal, like a very strange geometric picture. And that's why we decided to give the first prize to Peter Richter. And the first prize was an apple man. So it reminded his talk on on fractals, but on the other hand, it was just a combination of 3 apples on top of each other. So it was a nice coincidence of food delivery and price and fractals. Germany was not a large, strong country before, say, 1871, since there were so many small countries like Saxony and Bavaria and Prussia, and they only united in 1871, and that's why such a, say, meeting of people singing together on the Wartburg was already influential to have a kind of unification of different small countries where they spoke German. Before you go to the real challenges like epigenetics and genetics or immune system and circadian clock, these are of course hot topics. If you combine circadian clock with the immune system and chemotherapy, this is perhaps the most important connection I see at this stage, but it's also perhaps the most difficult area of research. Problems exist at any time. So there was the problem of socialism, falling walls, and so on. And there are problems of complicated science, there are problems of positions in academia. At the end, you have to be positive, you have to enjoy science, but it's also important to have a plan B, since there are not enough positions in academia, and that's why also other, say, positions in society are quite important, and why not to go to industry, to artificial intelligence, or to social issues, that these are also interesting topics. In the mid-90s, I realized that I'm no longer a physicist, and I'm not really a biological or biomedical researcher, and I became a bit nervous. But then I realized I published enough papers, that's why I might even get a position in the US at a medium university. And this was at the end my plan B. If I cannot make it in Germany, then I would go with my family to the United States. There is a hierarchy of universities, and that's why I was quite optimistic that I get positions in perhaps at a teaching university at least, to enjoy teaching and to enjoy interdisciplinary research. In fact, I got a couple of letters that people said, okay, aren't you interested to come to Utah or to Montreal? But at this point, I got already my position here in Berlin. Stay optimistic, enjoy science, and you can also contribute to science.